So first of all, thank you all for being present here in my thesis defense. I'm going to talk about my work, AI for air quality, modeling, sensor placement, and source detection today. So as some of you are aware, air pollution is a deadly problem. And why I used some of you is because air pollution is not as actively discussed as the other problems. Here are some facts. 6.7 million people prematurely die because of air pollution. And 99% of the world, which is like the entire world, breathes unsafe air. So now we can think, sorry, yeah. Okay. And the pie chart here shows the causes of death due to air pollution. So 70% of that includes heart disease and stroke. So if some of the people getting heart disease and stroke, that is probably because of the air pollution. Now, the most affected regions by air pollution are the South and East Asia. And out of top 50 countries, out of top 50 cities which are polluted, 35 of them are from India and 9 of them are from Pakistan. So we can see that the scale of the problem is mostly focused on the India. Now, when we talk about pollution, we generally talk about PM 2.5, which is particulate matter 2.5. Now, why this pollutant is important is because it is the cause of most deadly diseases that happen. It is smaller than the human air and it can easily penetrate through the lungs and enters the bloodstream. The major sources of PM 2.5 are vehicular emissions, industrial processes, and others as listed here. Vehicles are also one of the major sources of PM 2.5, which is included in this thesis. Now, WHO guidelines are suggesting that the annual PM 2.5 should not be more than 5 microgram per meter cube, which is quite a challenging bar to meet. Cities like Delhi in India, they have about 100 microgram per meter cube annual averages, which is quite higher than the WHO guidelines. There are several national programs like India's NCAP, China's Blue Sky Initiative, and Pakistan Clean Air Action Plans, which are being implemented to curb the air pollution. But where is the challenge? We can't really manage something which we cannot measure. So the first challenge here is the sparse monitoring networks. The second is we don't know which sources are contributing to air pollution so that we can curb them. So now the question is, how can we tackle the air pollution using the AI techniques? In this thesis, I am mainly focusing on 3 verticals. First is, where is the pollution high or low? So here high and low means that where are the most affected regions by the pollution. The second problem is where to place new sensors. And the third problem is where are the pollution sources. To tackle each of these challenges, I am going to propose 3 AI solutions as 3 chapters of the thesis. First, I'll start with the first one, which is air quality modeling using Gaussian processes. India has about 550 stations for about 1.4 billion people, which is much lesser. Experts suggest about 8,000 stations requirement in the country like India. These stations are also concentrated in the urban areas, as you can see in this image, and rural and semi-urban areas are largely unmonitored. Now, due to the consequences are that we cannot assess the exposure at the fine-grained granularity at other areas of India. And whenever the policy decisions are made, they are based on the incomplete data. So what is the solution? We have to have the solution which can give us the air quality estimates at each and every place in the India. That's why air quality inference. This work was published in IIIT 2022. Now the problem setup looks like this. We have certain air quality stations spread across an region of interest, and we have certain weather stations from where we can get the meteorology data. And our aim is to predict the PM 2.5 at unmonitored locations, and we also want calibrated uncertainty. Now you may ask why we need uncertainty. Is because policymakers would rely on the uncertainty estimates to take the decision. Now, traditional interpolation methods are quite simple and they are unable to model this complex behavior. They also don't provide the uncertainty estimates. Other machine learning approaches such as random forest, XGBoost, they provide better accuracy than the interpolation methods, but they still don't provide the uncertainty quantification. Now, there have been related work in this field where are deep learning based methods and co-training methods which are being used. They provide the state-of-the-art accuracy, but they don't provide any principled uncertainty and they remain black box, which means if we know certain things about the field, we cannot induce that domain knowledge into the modeling. Thus, there is a gap which needs a model that provides both the accurate predictions and calibrated uncertainty. That's where we move to Gaussian processes. Now, the intuition behind Gaussian processes is like this. It is a distribution over functions and not just the parameters, which means that if you have no data, then you will see something like the left-hand side figure, where we can draw infinite number of samples from the Gaussian process prior. But as soon as you see some data, which is shown in the black dots in the right-hand side, we get a posterior distribution, which provides us the estimate at every other place and also the uncertainty. Mathematically, Gaussian processes are defined as a collection of random variables and any finite number of which have a joint Gaussian distribution. It is specified by a mean function which provides us the mean estimate of any phenomena we are trying to model, and it also has a covariance function which helps us model the uncertainty of the phenomena. Now, the heart of Gaussian processes are the kernel functions. The most simple kernel function is the radial basis function or the squared exponential, which formula looks like this. It is sigma square exponential negative x minus x test square divided by 2L square. Now, here two important parameters are sigma square and L square. L is known as the length scale. Length scale controls how smooth our data is, and based on that, it will be learned during the optimization process. In this visualization, we can see that as the length scale is smaller, if we draw the samples from the GP, they look less smoother compared to a larger length scale, which is on the rightmost side. There are other possible families of kernels, which is Maton family, which is used for more fine-grained control over the kernels. Now, a good property about kernels is that we can sum multiple kernels to achieve desired behavior. For example, this figure shows that we can combine or take a sum of a linear and periodic kernel to achieve something like the lower right plot here. Right? We can also do the product of kernels to achieve the desired behavior. For example, here we are showing linear into periodic. I'll show in the next slides how we make use of this phenomena. Now, the first challenge that we get while modeling the air quality is non-stationarity. To understand it simply, we can think of a large terrain where there are no obstacles, so that the air quality will more or less remain similar. But if you go to some areas where there are mountains, then air quality will suddenly change from one values to the other. So it means that if we mathematically say, then the smoothness of the function is varying across the space. And for that, we need a non-stationary behavior into our modeling. To check if our data has this behavior or not, we did an experiment where we empirically computed the covariance matrix and then interpolated it across the entire space, and which is shown here. So if our data was showing the stationarity behavior, we would see that the covariance between the point T and A and T and B should be similar, but it is not here. We can see that the values at B are smaller than the values at A. So this motivates the need for a non-stationary behavior into our modeling. To solve this, we use something called as Gibbs non-stationary kernel, which allows us to learn the length scales which vary with the input points, which means that we can learn separate length scales at A location and B location, so that we are able to model this complex behavior, which would not be possible with the stationary kernel. The second challenge is that usage of the categorical variables which might be available in the dataset. In typical Gaussian process kernels, we compute the Euclidean distance between the features, which is not possible in the categorical variables. So we use something called as Hamming distance, which just gives it 1 if the feature matches, or it gives 0 if it doesn't match. So we replace the Euclidean distance by the Hamming distance here. The third important challenge is the temporal pattern. Air quality shows the diurnal and seasonal cycles, which we can model using something called as locally periodic kernel. Here we are multiplying the periodic kernel with the RBF kernel so that we can allow for variable amplitude over the time and also account for the periodicity which is inherent in the air quality data. Combining all these three kernels, we propose our final kernel, which is the multiplication of all this. When we do the ablations over this model, we define the ANCL notation, where A means that ARD, which means that we want to learn the length scale separately for each feature or not. The second part is non-stationary kernel. If it is enabled, then we use a non-stationary kernel. If it is disabled, we use stationary kernel. The third is categorical kernel, where we use the Hamming distance. And if it is disabled, we just convert the features to one hot encoded format and use the Euclidean distance. And fourth is locally periodic kernel. If this is disabled, we just use the RBF kernel for the time feature as well. Now, another challenge with the modeling was that scalability issue. With our data, we were not able to fit the model into the GPU RAMs. So we leveraged a recent work from NeurIPS 2020, which allows the batch-wise stochastic gradient descent in the correlated settings like Gaussian processes. In the experimental setup, we did experiments with two datasets, one from Beijing, another from London. Both of them had the hourly data, and particularly Beijing had the high pollution variability compared to London. We compared the results with other baselines like random forest, Adane, which was the state of the art at that moment, and our ablations, as I explained earlier. The metrics here that we track are the root mean squared error, which will give us the estimate of like how well our mean estimate of the Gaussian process is good. And the second metric is the negative log likelihood, which measures how well our uncertainty estimates are. Now, looking at this figure, we see that our method ANCL achieves the best RMSE among all the other methods. And when we look at the ablations, we see that as we enable more and more components of the proposed methods, we see better and better NLL. And at the end, when we enable all ANCL configuration, we see the best NLL here. The same behavior is visible in the London dataset as well, but the variability is not much because the dataset itself has low variability. Now, the key takeaway from this is that we have proposed a non-stationary GP with domain-specific kernels, which outperforms the standard approaches for PM 2.5 prediction. Our contributions include Hamming distance kernel for categorical variables, Gibbs kernel for spatial non-stationarity, locally periodic kernel for the temporal patterns, and we achieve the best uncertainty calibration using the ANCL configuration. Now, what we have achieved thus far is the accurate PM 2.5 predictions at unmonitored locations along with the calibrated uncertainty estimates. But the challenge here is that our predictions are relying on sparse sensor networks, which may not be enough to allow our modeling method to perform well. We will always get high uncertainty as we go far from the sensors. So we need more sensors for better coverage. So next question, where to place new sensors to maximize the coverage with minimum budget? And that's where we move to the next chapter of my thesis, which is about the sensor placement problem. This work was published in IIIT 2026, where we proposed a fast method to do the optimal sensor placement. Now, starting from the ground one, like, can't we just place the sensors uniformly? And the answer is no, because pollution varies spatially and it is not uniform. Some regions have more variability than others, so we will benefit if we install the sensors intelligently across the space instead of doing it uniformly. And also each of these sensors are costing about 1 crore Indian rupees. So we have the limited budget. So our goal here is to maximize the information gain from each of the sensors and avoid the redundant placements. The problem formulation is like this. We have XC and YC as the existing monitoring stations and the PM 2.5 readings coming from them. XT specifies the target grid where we want the good performance or good reconstruction error, we can say. Now, for example, XC for context of India would be 500 because we have about 500 sensors in India. And XT we can define as the entire India as some 0.1 resolution grid level. That's where we are interested in maximizing our information gain. Our mutual information objective looks like this. Mutual information says that when we have the entropy given our current locations, what is the reduction in the entropy when I include a new sensor? That's why the first term minus the second term, and second term is the reduced entropy after installing a new sensor. If we maximize this objective, then we are essentially maximizing the information gain over the space. Now, since the first term does not depend on the X new, maximizing this entire term just reduces to minimizing the second term alone, which is the uncertainty given the existing sensors plus a new sensor. Now we will look into the complexity of the existing methods using the same mutual information objective. If we directly try to use the exact mutual information, then we have to try out all the n choose k combinations, which is prohibitively expensive. Then there is a greedy version of this approach, which works in order nk time, and it provides about 67% of the performance with guarantees. The third option is the maximum variance, which is very fast and just works in order k time, but it does not give very good performance. So now the challenge is that can we achieve something very fast, accurate? That's what this work is about. Key insight is that we want to change the problem from a discrete optimization to a continuous optimization. Traditionally, in each of these three methods that I talked, we use a discrete grid like this and try out each of the locations from this grid into the objective function to figure out where it maximizes. But if we can just convert this to a continuous problem where we assume the coordinates of the sensors as the learnable parameters and optimize them in the coordinate space, then we can make this process much faster using the gradient descent. And that is the crux of this work. Now here, as we do this, our runtime gets independent of the grid size because there is no grid anymore. The method overview looks like this. We provide the input as the sensor locations and the data available at that point, and we give a budget to the model. We initialize our trainable parameters as x new, and we pass to a surrogate model, which we will talk about in a minute. And then we run this optimization process, which will go and optimize the locations of the new sensors. And then after the convergence, we get the output as our optimized locations where we would like to install the sensors. The loss, to be exact here, becomes the log variance of any model that we choose, and models could be something like Gaussian process or a neural process, which we will see. Here in this formula, DC is the existing sensor data, and X new and Y new are the new sensor locations which we want to optimize. Now, one caveat here is that Y new is not directly available because we have not yet placed the sensors there. So as a proxy, we can just use the predicted values at those locations. Now, another problem is that when we run this optimization, the sensors may run out of the region where we cannot place the sensors. To solve that, we use something called as out of region penalty, which is this scary looking formula, but it is very simple. All we need to do is whenever a x new coordinate is trying to go out of the space, we measure its closest coordinate here and see if it is at least greater than delta. If it is greater than delta, which can be our grid size, then we apply the ReLU on that, which will make it positive, and then we apply the exponential, which will exponentially penalize that if it goes out of the bounds. So this additional particular loss that we add here will ensure that our sensors will stay within the boundary that we define. So our total loss becomes something like L variance, which is the variance loss, plus lambda into L out of region loss, where lambda is a hyperparameter. In our experimental setup, we are using a continental scale PM 2.5 data over India, which is a satellite derived PM 2.5 from 1998 to 2018. It is available at 0.1 to 0.1 degree resolution. We divide that into train, validation, and test as specified here. Now, for this method to work, we need a surrogate model, which can be a neural process model or a Gaussian process model. To decide which model is best for our experiments, we do an experiment on training the model and then checking the performance on the validation data. These are the same metrics that we were using in the earlier work. One is the RMSE, another is negative log likelihood. We see here that in both of the cases, the TNPD model, which is the transformer neural process variant, which works the best here. So we go ahead with that model for the rest of the experiments. Now again, looking into the time complexity as we discussed earlier, the GDMI's time complexity reduces to order m, where m is the number of iterations you would take for gradient descent to converge. To materialize this, we also checked the runtime for 9 sensor placement in a medium scale experiment, and we found that greedy MI takes 25 minutes, where our GDMI method just takes 10 seconds, which is about 148x improvement over the method which is practically being used in the practice right now. We compare our method with other baselines like random placement, maximum variance, which is just placing the sensors at the highest uncertain points, and the greedy MI, which is currently being used practically wherever it is tractable. For the India scale experiment, even greedy MI was intractable in our experiments. The first result plot is looking like this, where we chose Madhya Pradesh as our experimental grid, and we tried to install 10 sensors here and saw the improvement in RMSE over time. We see that MI, which is the greedy MI here, performs the best as expected. Then our GDMI method, which is shown in blue, is also very close to the MI and with some constant gap. And we see that random and maximum variance are not able to do very good. In our continental scale results, we were not able to even run the greedy MI because it would have taken about 60 days to run. So we just ran the maximum variance, GDMI, and the random, and we can see that GDMI is doing very good compared to the maximum variance method. Here we see the qualitative comparison, which means that we want to qualitatively see how the sensor placements are. We can see that all the blue dots which were placed by the maximum variance are mostly at the boundaries of India, and that is because uncertainty was the highest at those points which were far from the data. But our GDMI method does not always place the sensors at the boundaries, but tries to cover most of the regions in a balanced way. There could be an extension of this method which includes the fairness aware angle, where the motivation is that the standard optimization may underserve the some populations. Population is not uniformly spread across the region. We can do a simple modification of our method, is that we apply the weights to the loss function, where weight is the population density. So it will penalize more where there is higher population, and we are more likely to cover many people in those regions. When we did these experiments, we saw that we get higher coverage in the densely populated area with minimum impact on the overall RMSE. So we can use this kind of different criteria as extensions to the standard method. Key takeaway from this chapter is that we have developed a 100x faster method than the information theoretic methods, with comparable placement quality. Key idea was to convert the discrete optimization problem into a continuous problem and treat the coordinates as the parameters. Here our runtime got independent of the grid size because there was no grid anymore. We used the out of region penalty to keep the sensors into the valid region. And also our method is surrogate agnostic, unlike some of the related work which was there. So this can work with any of the method, GPs, neural processes, and any other which can allow the gradient descent to backpropagate through it. Now we are coming to the next question, which is where are the pollution sources? Which is the third problem of my thesis. This work was published in the ACM Journal of Computing and Sustainable Societies, which is Space to Policy, Scalable Brick Kiln Detection, and Automatic Compliance Monitoring with Geospatial Data. Now looking at the scale of the problem, India is one of the largest brick producers with 233 billion bricks per year. We are estimated having about 1 lakh brick kilns nationwide, and we have employed 15 million workers which are working in brick kilns across the nation. Experts have checked that about 8 to 14% of the contribution in air pollution comes from brick kilns, and major sources are PM 2.5, SO2, and CO. But there is no comprehensive registry of brick kilns which exist till moment. Now, before going further, we will just look into the three major brick kiln technologies. The first one is called circular fixed chimney bull trench kiln, which was the old technology being used in India and other parts of the Asia. Then there was an improved technology called FCBK, which just changed the shape of the brick kiln to an ovular shape. And then there is a much efficient technology called as zigzag, which provides up to 70% cleaner emissions. Now, since we use the object detection techniques to detect the brick kilns, first let's see about some of the basics of it. We use two types of object detection boxes. One is axis aligned bounding box and other is the oriented bounding box. So as you can see, if this orange object is brick kiln, then axis aligned bounding box will overestimate the area of the brick kiln. But if we use something like oriented bounding box, we will get a very close estimate of the area of brick kiln, which can provide us some idea of the capacity of that brick kiln, which could be useful for the policymakers. So in our experiments, we choose to go with the oriented bounding boxes. For the data sources, we used two data sources. One is from the Planet Labs, which is available at 4.7 meter per pixel resolution, and A3's Wayback Imagery, which can go up to 30 centimeter per pixel. We used the A3 imagery for annotation and validation, and we used Planet Labs for detection. Now you may ask that why not just train on the A3 imagery, which is available at much higher resolution. That is because the terms and conditions of A3 prohibit mass download and training of their imagery. So we had to find a workaround which was provided by the Planet Labs. Now the first challenge is that to detect the kilns, we need some initial data to train our models on. So we start with 4 diverse regions. First is Delhi airshed. As you know that Delhi is the most polluted region. Another is Lucknow. The third is West Bengal, and fourth is the Ahmedabad region. In the initial round of this, we annotated 1,621 kilns with 125 hours of annotation effort. For model, we chose YOLO family of models as our choice, and we experimented with different variants of YOLO and to see that which variant works the best in our experiment. Here we found that YOLO 11 medium OBB provided the best mean average precision in our case. So we choose that for all the experiments which are from here onwards. The iterative training pipeline looks like this. We did the initial training on the 4 regions that I just spoke about. We run the inference on the new regions. We do human validation, which means that we correct all the false positives, and we verify if there was a classification error, which means that if the model predicted a CFCBK as FCBK, then we would manually correct that. Then we retrain with the expanded dataset and repeat until the convergence. After doing this process, we were able to detect about more than 30,000 kills across 5 states of India. And here we show the category-wise distribution of brick kills across 5 states. We can see that CFCBK is predominantly present in the Uttar Pradesh, and zigzag adoption varies across the states, where Bihar is leading with 73% and UP is with 34%. Here is the spatial distribution of the CFCBK, which is another angle to look at the distribution. To check if our counts are correct, we validated them against the government surveys, which provided 94% correlation for the UP and 76% for the Delhi. For West Bengal, we got 84% correlation with the government surveys, which means that we are getting high correlation with the surveys and our counts are close to the complete counts. Now we come to the compliance monitoring, which means that once we have the exact location of brick kills, what more can we do to help the policymakers? There are certain distance requirements from various different objects defined by each of the state. Here the criterions are like, there should be a minimum distance between 2 brick kilns. There should be at least some distance from the habitation, hospital, highway, railway, and all those things. And this table shows the distance requirement for each of the state. This also specifies that each state has their own rules, and these are not governed by some scientific surveys, but sometimes chosen ad hoc. When we ran the compliance on the kilns, we found that about 70% of the kilns are violating at least one of the compliance rules. We were able to identify the objects from the OpenStreetMap data and compute this. Top violation categories are the inter-kiln distance, hospital proximity, which is alarming, and third is the habitation proximity. If we look at the population which is living within 800 meters of the brick kilns, which is the criteria set by the central government, that there should be no brick kiln within 800 meters of the where people are living, then we see that this is a massive number of 30 million, which is more than the population of Australia. We also checked the technology evolution, which means that in different regions of India, how quickly or slowly they moved to the better technology, which is zigzag. We saw that in Delhi, about 2018-19, there was a huge change where many brick kilns converted from FCBK to zigzag, which is clearly visible from the left-hand side plot. In the Lucknow airshed, we can see that the adoption started very early in 2010, and then it plateaus out as we go towards 2022. We can do certain this kind of experiments in different regions of India to find out where the technology adoption is already there and where we need more intervention to support people going to the better technology. We also did a case study on Delhi to see what is the impact of brick kilns in the Delhi's pollution. From the WRF ChemX modeling, with help of one of the air quality expert, we found that brick kilns contribute about 8% of Delhi's PM 2.5, which is significant source. If all of these kilns transition to zigzag kilns, then they will be emitting 70% less pollution than FCBK, which can help reduce this 8% contribution to a lot. We can also get something like the emissions in tons per day by state, because we have the total counts for each state and we know the emission rates for each of these pollutants for each brick. So putting up the math, we will be able to get this kind of numbers also, which is useful in some of the studies. Now, policy implications of our work is that we are automatically identifying and prioritizing the non-compliant kills. We are also tracking the transition of technology from the less compliant to more compliant technology. We have checked the population exposure near the brick kilns, and we have also prepared the emission inventory, which can help in other studies. Key takeaway from this work is that we were the first to create a comprehensive brick kiln dataset of about more than 30,000 kilns, and we also did the automatic compliance monitoring across 5 states of India. So summarizing the thesis, it goes towards 3 problems: modeling air quality, sensor placement, and detection, which provides a unified framework from probabilistic inference to optimal monitoring to source identification. The impact is that we provide the actionable insights for data-driven air quality management to the policymakers. Now coming to the future directions. For the air quality modeling, there are many big data resources nowadays available, which can be used as features in the modeling to improve the accuracy of the model. We can also do the real-time forecasting with uncertainty, which can help us plan certain things well. In the sensor placement problem, we can use the equity-aware placement, which we already discussed, and we can also do the joint optimization for multiple pollutants. In the current work, we just did this for PM 2.5. In the source detection work, we can also try to detect other sources of pollution like vehicles, industries, stubble burning, and we can also automate the temporal tracking process of the kiln technology evolution. These are the publications which were part of the thesis. And in the end, I would like to acknowledge the help from many people across the journey of my PhD. First and foremost is my advisor, Professor Nipun Batra, who has helped me with all the ups and downs of my PhD. The second acknowledgement goes to the committee members, Professor Anirban Gupta, Dasgupta, and Professor Udit Bhatia, which have helped me with their feedback at various stages of my PhD. I would like to thank the examiners and anonymous reviewers, my collaborators, Dr. Kevin Murphy, all the domain experts, Sharath Guttikunda and Samir Maithal. Without their help, this work would not have been possible. The lab members, Rishiraj, Rishabh, Ayush, and many others, which I could not include in these slides, my family and friends, and various funding agencies, and all the people who have contributed to this work and supported me over the time of my PhD. Thank you, and I'm open